Welcome to all. So today we are going to discuss about few important feature and aspects of nuclear reactor. Mainly we'll concentrate on a fast reactor, fast spectrum reactor. So this is a very short discussion or explanation, whatever you can say. I have made one small presentation on that. So the heat generation in fast reactor, it can take place broadly in three ways. We know the major things is contributed by fission, and the reactor materials like all, say, the fuel pins, the control and absorber rods, all these things, the reactor materials absorb some of the gamma rays produced during fission, and this converted to thermal energy. And lastly, the decay heat. It's due to radioactive decay. So this decay heat is the heat which is released as a result of radioactive decay, which can take some quite time. Okay, so this heat is produced as an effect of radiation on materials. The energy of alpha, beta or gamma is converted into thermal movement of the atoms. So this graph shows how gradually, after the shutdown of the reactor, how the decay heat gradually reduced. So this is the peak actually at T is equal to 0. Okay, so this is approximately 6.5%. So this 6.5% heat is to be removed if there is auxiliary failure, or there is a scram, or you due to some reason you shut down the reactor. So this 6.5% of the total heat, it is to be extracted. So this means if the reactor capacity is, say, if it is a 500 megawatt, so 500 into 6.5%. So 500 into 6.5 means 5 and 32.5. So around 32 megawatt will be the decay heat. It is to be removed. So for that, say if there is a 2 loops and each loop having one primary heat exchanger, so you need total 4 decay heat exchanger. So definitely it should be a passive device, means there should not be any active component. So that means, what I mean to say, this decay heat exchangers should be naturally cooled. It's due to all the flow should be in the tube and shell side. Shell side it will be air, so it will be due to thermal siphoning. So once it is from the bottom, it will enter the cool air, and once it is heated up, then the density of the air will reduce, which will gradually go up, and this will this will establish the flow in the shell side. So this is the typical cross-sectional view of fast reactor. So you see, this is the active core. So here only pure fissile material will be kept, and this is the axial blanket, this is the radial blanket, then there will be a reflector, okay, and this is the gas plenum, means that we'll see in each fuel sub-assembly. If you see the geometric structure of the fuel sub-assembly, there also this is kept, because this the gases produced during the fission, it will be accumulated here, okay, accumulated here, and these are the shielding, this is the shielding, and these are the this is the shieldings, axial shielding, and this is the radial shielding. Now we will here I would like to specify, I would like to mention a few points. Anyway, my English is not good. I am a Bengali, so I tried. I have written what. Hope I'll be able to explain that. So if you see the cross section, it's of a fast reactor, unlike light water, unlike thermal reactors. There is no this cross section of fast reactor is quite low. So there is no large reactivity change of the core due to accumulation of fission products, because the cross section is low, okay. The core materials have low cross section for naturally all the reactors, but in case of fast reactor, it is, if you see that this is called the total macroscopic cross section for fission. So if you see my first lecture on nuclear physics and basics of fission, there I have explained. So in case of fast reactor, that is 2 barn, and in thermal reactor it is 500 barn. So it is around 250 times the macroscopic cross section, okay. So in order to sustain the same number of fission in both fast and thermal reactors, so as to generate the same thermal power naturally, because the cross section is less, so you need higher enrichment, okay. So the enrichment is in fast reactor fuel is 20% higher than thermal reactor. It's because this enrichment is required to obtain the criticality. So that also I explained in some video, how to find out the critical mass and critical volume, why that concept, why this called criticality and all. So this is the this graph is representing the energy distribution in the active core and the blanket at beginning of the cycle and the end of the cycle. So normally from the blanket, if you see, it will gradually increase, and it is become same as the active core. This is the peak, okay, here and here. So this is the energy, the power distribution, the power generated due to fission in blanket as well as the active core. Okay, this is the comparison. This is the comparison of thermal reactor and fast reactor. Okay, here you see it is much more, the enrichment is much more higher, and the neutron, because it's a fast neutron, this is thermal neutron, so it will be much more. How much time? 100. This is 25. This is 100 divided by 0.025. 0.025 মানে 10 to the power minus 3. ঠিক আছে? Then this is 4. তার মানে 4 into 10 to the power 3 times higher. No, it is kilo electron volt. So 4 into 10 to the power 6. That much times higher the neutron, the average energy of the neutron. Okay, and the energy extracted also accordingly it will be definitely higher. The neutron flux is higher. The core power density is higher. All these things are higher in case of fast reactor. Okay. So to maintain the high energy spectrum of the neutron, the core should be as compact as possible. So, which in turn implies that the core volume of the fast reactor will be much more lower than the thermal reactor. Okay. This is the power density, and this is the linear power rating. So as these things are much more, these all parameters, the energy extracted from the fast reactor as well as the average power density and the linear power rating of the fuel, this is much more higher than the thermal reactors. So we need very efficient coolant so that the heat will be extracted very efficiently and rapidly. So that's why this is the main reason to use sodium, the metallic fuel. You know, this metallic fuel having the high thermal conductivity. So, and other heat transfer. This means the liquid metal having enhanced heat extraction capability. So that's why in case of fast reactor it is obvious to use liquid metal as a coolant. So this is a figure. It is the x-axis. Here we can understand the transient, how fast. Let me explain it. So how to draw something? Yeah. Arrow. I don't know. So if I want to draw one line, then from here to here, here, and here, and here. Anyway, what I mean to say, I have written here. I will read it. the core of fast reactor is not most reactive configuration. Okay, that is, if there is any disturbance in the core configuration, or if the core is melts down, then there is a possibility of reactivity increase due to core compaction. Means वो accumulate हो जाएगा, means there will be a compaction and the reactivity will change. Okay, so this aspect is to be considered to analyze the safety criteria of the fast reactor, but which is not there in fast thermal reactors. So in they are only because the moderator is there, correct? So only a particular moderator to fuel ratio will keep the reactor in the most reactive configuration. So if there is any change in the core configuration, definitely there will be a decrease in the reactivity. So which will not see the transient. But here there is a possibility to see the transient, because in case of disturbance, perturbation, or in the if the core melts down, then this sudden increase of reactivity will be there. And if this is crossing this one, and you see this is for the fast reactor, if you see the period, this is from here to here, it is much more this is very fast, and here it is from 10 to the power is. So what I mean to say, from here to here it will take slight more time, but for fast reactor it is very quick, because this 10 to the power minus 3, this scale is 10 to the power minus, here it is 10 to the power minus 4 or somewhere here. Okay, so if the reactor attain the uncontrollable state, under such uncontrolled situation, the fast reactor has a shorter period compared to thermal reactor. Okay, however, under the controlled state of the reactor, means left hand side of this line, because here reactivity is 1, this side. So the period are practically same for both fast and light water reactor, and it is not distinguishable. Okay, and the periods, and here you see from 0.1 to this one, it is so long. You see, it is 10 to the power 3, 10 to the power 3 second, and whereas it is coming in millisecond. So normally these things, typically I can tell, this is this will happen within 3 to 4 milliseconds, and this is around 8 to 12 milliseconds. Okay, so what I mean to say, the reactivity is less than 1, that side, so it is, the time is so long that the control is quite possible with technically with very simple mechanical regulating units. You need not to have any feedback, or means, I mean to say, the control is much more easier. You can tell it's more or less it is in steady state. That only I mean to say from this few lines. Okay, so now coming that if it is higher than reactivity is higher than 1. Okay. So then the prompt neutrons determine the time behavior of the reactor, which is called super prompt criticality. The periods are for both the case in light water, in pressurized water, pressurized heavy water reactor, or you can tell thermal reactor and FBR and fast reactor. So the time period is too short. So which to avoid such condition, that means from here to when the exponential increment of reactivity initiated, before that you have to shut down. So you need a very fast shutdown. Otherwise it will become bomb. Means it will go uncontrollable state. So that's every reactor must be designed so that the super prompt critical condition cannot occur in any condition. We have to consider that, and you have to assume that this super prompt criticality should be a hypothetical event. Okay, you can consider these things as a design consideration, but it should not happen. I mean to say that. Okay. But if this super prompt critical condition is arrived or postulated, it is shown that it is now if super prompt criticality occurred, then your closed loop highly feedback, it's needed that feedback effect. Okay, so for that the Doppler coefficient will play a prominent role. So in my previous lecture, the reactivity estimation, I have told what are the feedbacks, that 5 feedback method and all. You can see that. Okay, and the neutron absorption capability of uranium-238 also it will take place. It will play a major role. Okay. So as in the fast reactor, the power density is high, so which is confirming the low thermal capacity of the core. That means H by MT. That means the heat required to change unit temperature for unit mass. So that is very low. Very quickly the temperature will shoot up. Okay. So that's why these consequences of the disturbance cause very fast temperature change in the core. So this will actuate the fast and continuous feedback by Doppler and fuel expansion effect. Okay. So, and another thing, the high power density means the small core dimension. The core dimensions are very small. So if you consider this, then by very short travel of the control and absorber rod drive mechanism. Okay, it can be controlled or shut down very easily. Okay, so this feature, even though it is seems like a transient effect, means the thermal capacity is low. Okay, but due to that the temperature may change very fast. Okay, very means you can very easily control the temperature. So even though it's a limitation, it's a disadvantage, but we can take this disadvantage for the better control of the reactor. Okay, so that's why the high power density of the fast reactor core is demonstrated as a safety oriented advantage. So this kind of disadvantage of the special feature of the fast reactor can be taken in consideration to augment the safety of the fast reactor. So this is the again I am showing the typical, these are the fuel pins. So this is the top plug and this is the bottom plug. This is the spring, and is the top blanket, and this is the bottom blanket. Is the middle plug, and this is the in the previous slide I have shown that gas plenum. So here only that all the fission gas will be accumulated, and these are the spacer wires, and this is the fuel subassembly. Here the coolant will enter, and on this is the foot where this fuel pins. These are the fuel pin, and this is the fuel subassembly. It will fix. So you see, this is the fuel pin. So this fuel pin, it will be fixed. It will be seat here. So many pins will be there. Okay. And this is the handling head. So during that what is called, the transfer arm will take the fuel and it will be located by the proper rotation of small and large rotatable plug. This subassembly will be placed in the particular position. Okay, that we all know. And this is the top shielding pin, and this view is it's a grid plate. On the grid plate, this is a single subassembly, how it will be fixed. Okay, so these are the two primary coolant pump. So this is the suction, means here it will be the suction is from the cold pool. So yeah, and it is from the cold pool, it will go to the grid plate area, and from there the flow will be that, means the discharge will be like this. So this will go, and that coolant will flow inside the fuel, and it will extract the heat, and it will enter the shell side of the primary heat exchanger, and the heat will be extracted because the secondary sodium will be on the tube side of the primary heat exchanger. It will be extracted, and again it will go to another heat exchanger, where this means steam generator, where the water Rankine cycle will be there, and it will generate the pressure which will be expanded in the turbine, and it will rotate. So this is the typical fuel configuration in fast reactor. And this is sorry, Okay, so this was all about the sorry, is the neural network. So this was all about the discussion of today. So some specific features of fast reactor I have explained. So hope it will be useful to you all. So thank you so much. Thanks for your patience.